So we got a lovely exam here. This is a calculus one, locally known as Math 1650 exam, spring 2025. It's the second exam of the semester, meaning we already know the basics of limits. We understand how to take derivatives. Now we're going deeper, harder derivatives and applications. And you know what that means? Word problems. Oh yeah, that's going to be fun. We've got 6 multiple choice and 4 workout, or in other words, long answer problems. So lots for us to do. But before we begin, as always, put our name, because we want to make sure we get the credit for all the great work we're about to do. And pro tip, make it legible. All right, let's begin. Number 1. Let y be a function of x defined implicitly by the equation y squared plus 2y minus 2 minus e to the x equals 0. And it says dy dx slash 0, 1. Now, a couple of clues. Implicit tells us what? Implicit differentiation. All right, so that's the big clue. This notation here means you're going to evaluate. So when you see a vertical bar, it's an evaluation. So we're going to find dy dx, then we're going to evaluate it at 0, 1. So in other words, we're going to plug in x equals 0 and y equals 1. Okay, so how do these problems go? Well, they always follow more or less the same story. Whenever we're thinking of implicit differentiation, we say, what we should do is we should think to ourselves, hey, y is a function of x. It even tells us that right here. Y is a function of x. And so, secretly, when we look at this, we don't write this down, but I'm going to write it down just to emphasize. It's y of x squared plus 2 y of x minus 2 minus e to the x equals 0. Now, take the derivative of both sides with respect to x. Y with respect to x, because this is dx, right? You know, what we're really doing is we're finding dx here with respect to x of y. So here we go. Where does the x show up? Well, we see an x there, but we also see it there and there, right? Because it's y is a function of x. That's what we're thinking. So let's start with this y squared. The derivative of y squared with respect to x. Well, chain rule. 2 comes down. Y to the first power times the derivative of y with respect to x, dy dx, plus 2 times the derivative of y with respect to x, which is dy dx. Derivative of minus 2, 0. It's a constant. Derivative of e to the x with respect to x, e to the x. And that equals the derivative of this side with respect to x. Derivative of 0 is 0. Now, we can solve, but we can also plug in. So we're going to plug in. So the question is, when do you simplify? Now, I like to plug in as soon as possible, but not sooner. And you might say, okay, well, how do I know? Well, are we going to do something with it after that point that needs the variables? The answer is no. Well, we're ready to do our plug in. So we say, okay, let's plug in. So we're going to plug in x equals 0 and y equals 1. So we're going to get 2 dy dx plus 2 dy dx minus e to the 0 is 0. Oh, okay, well that becomes 4 dy dx, and this minus 1 can move across, equals 1. So dy dx is 1/4. There it is. All right, nice. Cool. All right, so implicit differentiation, nothing to be afraid of. Take the derivative. Remember to think of y as a function of x. Evaluate, simplify. Life is good. All right, number 2. Choose a function with no critical point at x equals 1. Okay, so there has to be no critical point. Now, where's the critical point? Now, because we're at 1, I tend to think of critical points as being 3 things, but one of them is the boundary. That's a little bit controversial. Different faculty have different perspectives of whether or not the boundary should or should not be a critical point. But for us, we say, okay, critical point is what? Well, we have either derivative equals 0 or derivative is undefined. So if we go through these and say, okay, what's happening? Well, I come up, I'm flat going up. There, the derivative is 0. Do you have a flat tangent line? Nope. Here we're flat, then we come out, we're flat. We can make a tangent line. Slope 0, no. Here, see, that's slope 0, critical point. Slope 0, critical point. Here, I have sort of a kink. And so what happens? There is no tangent line at that point, which means the derivative is undefined. All right, critical point, so it's not that one. All right, now here, we say, oh, it's pretty smooth. And if we sketch a tangent line, it's not flat. Okay, so that's not a critical point. So that's going to be our answer. And finally, if we come back, just to be sure, here we see it's sort of going up at an angle, and then it's steep. In other words, there's another kink. And so that's the place where the derivative is undefined. So that's out. So the answer is B. Ah, BB. All right, well, it can happen. It can happen. Now, on to the next one. Number 3. Find the derivative of the function. G of x is arcsine cosine squared of x. Now, this is sort of an onion problem in that we have layers. The outside layer is arcsine. And then the next layer is the square function. And then the last layer is cosine. Right? There's really 3 functions coming into play here. And so we have to make sure we account for all of them. So let's be extra careful. All right, now you might say, do we remember these derivatives? Well, good news is if we don't, we can look them up. So for example, derivative of arcsine, that's one that might require a lookup. That's 1 over square root of 1 minus t squared. Formula sheet, life is good. Bob's your uncle. Okay, so let's begin our function. And just to emphasize, arcsine of, and this is cosine of x squared. So, start with the derivative of the outermost layer. Derivative of arcsine, 1 over square root of 1 minus the inside squared. So, g prime will look like 1 over the square root of 1 minus this cosine of x squared squared. And if you take that cosine squared squared, this is really cosine to the 4th x. So you should have square root of 1 minus cosine to the 4th x. So that has it, that has it. That doesn't have the square root. That has cosine squared, not cosine to the 4th. And here, you'll notice, this is an interesting one because it says, hey, you forgot to plug in the inside. So that's why it's very tempting, but don't fall for it. Remember the chain rule. It's the most important rule, but we're not done. Okay, now we are moving in. So I'll switch colors here. What's the derivative of the inside? Well, I'll start with the square function. The 2 times cosine of x to the 1, right? So the 2 comes down, cosine x to 1. Are we done? No. Because then what? Then you have to times by the derivative of the inside. Derivative of cosine, negative sine. And now we're done. We've peeled our onion all the way. So upstairs we have a minus 2. I'll write it as sine x cosine x over the square root 1 minus cosine squared squared is cosine 4th x. And that looks a lot like B. Yep, there we go. What happened to A, by the way? A says, oh, you successfully went through 1 layer, even got through 2 layers, but you didn't take your 3rd layer, right? You said, oh, I forgot the derivative of cosine is negative sine. And so be patient. Be patient. It pays off. All right, well, another B. B, 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 B. All right, I think we're going to break this. Let's find out. Use the linearization of h of x as the square root x squared minus 5 at x equals 3 to approximate h of 3.02. Now there's a big word here, linearization. It's going to be a hard word for me to say sometimes. And that word is also known as tangent line. So if you see a linearization, think tangent line. There's a clue, right? Because the linearization starts with line. So there's that connection. So you say, find the tangent line of the function at x equals 3. So here's our function. And I would start by saying, let's make this calculus friendly. What do I mean by calculus friendly? I want to replace the square root symbol using an exponent, upstairs in the notation, because that's how our rules for derivatives are based. So it's going to become x squared minus 5 to the 1/2 power. All right, so h prime of x is the 1/2 comes down, x squared minus 5 to the 1/2 minus 1, that's minus 1/2, times the derivative of the inside. The derivative of the inside is 2x. Well, the 2 and the half cancel, and so this becomes x. Now we can convert back over square root x squared minus 5. It's downstairs because of the negative, and we can also convert back here. And I say convert back because we're a little bit more familiar with this notation when we do evaluation. All right, well, we got to plug in x equals 3. So, right, we have h of 3. That's the square root of 3 squared minus 5. 9 minus 5 is 4, and the square root of 4 is 2. H prime of 3, well, that's 3 over the square root of 9 squared minus 3 over 2. All right. So our tangent line is going to give our linearization. So how do you find it? Well, it's h of 3 plus h prime of 3 times x minus 3. So there's the tangent line. For us, that becomes 2, which you'll see most of these are very close to 2. And now this is the important part, plus 3/2 times x minus 3. All right, good, good. Now, here we go. We plug in 3.02. And if we do that, what do we get? Well, we get that h of 3.02 is approximately 2 plus 3/2 times 3.02 minus 3. Well, okay, that's approximately 2 plus 3/2 times 0.02. All right, great. Now, 2 divided into 0.02 gives us, hey, this is approximately 2 plus 3 times 0.01. And we're like, so that is going to be approximately 2.03. And there we go. All right, so we're looking for 2.03. And it's D. It's not B. See, sooner or later, it had to happen. All right, but the key here, if you see linearization, think tangent line. You're good to go. All right, moving on. Number 5. Given y is natural log of x plus 1 over x plus 3, find dy dx. Now there's 2 ways to go. And one is, do you love quotient rule? And the other is, do you love logarithm rules? And it's up to you. So we can do both. We have time. We're doing great on time. So let's suppose you love quotient rules. So if you do, you say, well, how do you take the derivative of a log of something? Well, you start by saying you take 1 over the inside. So it would be x plus 3 over x plus 1 times the derivative of the inside. All right, so this is 1 over the inside times the derivative of the inside. Now, here's where your quotient rule comes into play. So you say, all right, so you take bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Here you see an x plus 3 cancels. And what do we have? Well, we really have an x plus 3 minus x minus 1 because the minus distributes. And the x's cancel, and 3 minus 1 is 2. So this gives us a grand total of 2 over an x plus 1 times an x plus 3. So we're looking for 2 and an x plus 1 and an x plus 3. All right. Now, that's if you love the quotient rule. Some people don't. So here's an alternative. Notice you can say, look, before I take any derivative, I can rewrite a log because I see a division, and division becomes subtraction. Now, take the derivative. Well, what happens? There's now much easier. It's 1 over the inside times the derivative of the inside, but the derivative of the inside is 1. Subtract 1 over the inside times the derivative of the inside. Okay, but the derivative of x plus 3 is 1. Now we say, oh, we need a common denominator, so that'll become x plus 3 over x plus 1 times x plus 3. I multiplied the first term by x plus 3 over x plus 3, minus x plus 1 over x plus 1 times x plus 3. Again, multiply the second term by x plus 1 over x plus 1. And what do you see? Well, we have our common denominator of x plus 1 times x plus 3. Upstairs, well, we get x plus 3 minus x minus 1, right? Be careful with that minus sign. The x's cancel, and we're left with 2 over x plus 1 times x plus 3, which is D. And so you have options, and you don't have to do it both ways. Pick the way you're comfortable with. Pick the way that you are confident you'll get the right answer, because that's what matters. Make sure you do everything to help yourself. So let's do the next one. Our last multiple choice. Wow, it feels like we just started and we're already near the end. Well, these things happen. Number 6. Let f of x be 3x to the fourth minus 8x cubed plus 17. Which of the following statements is true? So they either have a local max or a local min, or no local extreme minimum at 0, and a local min, a local max, or a local min at x equals 2. And then there's an option where it says, oh, haha, there are no local extrema. All right. Well, so we're local max, local min type things. So we say, okay, let's begin. We start with our function. And first thing is we're going to find critical points. We have a strong suspicion of where they'll be. 0 and 2. Well, let's see if that actually is true. Take the derivative, and we get 12x cubed minus 24x squared. Yes? Right? Bring the 4 down, bring the 3 down. Now you can factor out a 12 and an x squared, and that leaves you with x minus 2. And the idea, well, it's never undefined. Polynomials are nice that way, so what does it equal 0? We see, hey, there's something happening at x equals 2, and something happening at x equals 0. All right, so it's true. We do have critical points at 0 and 2. Now, classify. For classifying, we have two options. There's the first derivative test and the second derivative test. Now, I'm going to go ahead and warn you that the second derivative test has limitations and it doesn't always work. And this is a case where it won't work. So I can see if I take another derivative, we get 36x squared minus 48x. If you plug in x equals 0, what's the conclusion? Well, the conclusion is that f double prime of 0 is 0. And the second derivative test says, I don't know. And that's it. That's all the second derivative test was. Sorry, can't help you. Try again. It's very frustrating when it says that to us. And we're just like, come on, second derivative test. Why do you think we're paying you all that, sweet, sweet money? So the first derivative test can oftentimes be a little bit stronger, but there's a little bit more overhead as well. So how does the first derivative test work? Well, we're going to sketch a line. So it's a bit of a sketchy situation. We mark our critical points, 0 and 2, and we start plugging numbers in. So let's suppose we plug in a big number, like 3. And we'll plug it into the derivative, and it's very useful to use the factored form. So I say, okay, let me look at it for this factored form. So if I plug a number like 3, and I get 12 times 3 squared times 3 minus 2, and right now I'm only worried about the sign. And I say, that's a positive sign, which means the derivative is positive. How about a number like 1? So I'm in between 0 and 2. Okay, positive, positive, negative. So I'm negative. What about a number below 0, like negative 1? Positive, positive, because you're squaring it, negative. So we're negative. Now what does that say? It says, we just read it off. We go down, and then we go down. It's like we're going down, down and down, we're going down. Woohoo! Now, what does that tell you? Well, it says 0 is not a local min or a local max. So it rules out A and B. Because, it says local min at 0 or local max at 0. Okay, so it's not that. Now, what about 2? All right, it says we're going down before 2, and then we're going up after 2. Down, up, down, up. What's happening at 2? 2 is a local min. So there's no local extrema at 0, but there is a local min at 2. Okay, so this says a local max at 2. This says no local extrema. So the answer is D. And there we go. B, 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 D, 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 D. Okay. Coincidence. Don't try to play the guessing game with your multiple choice. Work it out. All right, number 7. Use logarithmic differentiation to compute the derivative of this expression. Y equals 2x plus 1 over x to the x. No credit will be given for other differentiation methods, and your answer should be a function of x alone. Do not simplify your answer. All right, now, how does logarithmic differentiation work? Well, there's a couple of ways to do it. There's a few schools of thought. So I'm going to show you my biased school of thought because this is the one that it's the easiest for me to carry out. So here we go. There's a nice formula. It's on the formula sheet. Might as well use it. It says if you want to take the derivative of f of x, well, that's equal to f of x times the derivative of the natural log of f of x. You say, okay, all right. And it's not so hard to verify by chain rule. So, okay, so that's the generic formula. Why do we call it logarithmic differentiation? Because we introduce logs. Why might we want to do that? Well, notice we have x downstairs and x upstairs. So that's an issue. But with logarithmic differentiation, the logs can pull things out of the exponent. And so that's why we want to learn logarithmic differentiation. It gives us another tool to help simplify things. All right, now with that in mind, we say, okay, so for us, we have dy dx. Well, this is the derivative of 2x plus 1 over x to the x. Okay? So the rule says rewrite the function in the front, 2x plus 1 over x to the power x, and then multiply by the derivative of the natural log of the function. Now we're going to take a second and say, but we can rewrite this. So let's rewrite this. What can we do to this expression? We have an x upstairs. And that x upstairs is going to go down. So I say, hey, this is the same as x, natural log of 2x plus 1 over x. But then we're like, whoa, wait. I see division inside the log. So this can be written as x parenthesis log 2x plus 1 minus log of x. And now we're like, great. That's a much simpler expression to take the derivative of. In other words, instead of having to take the derivative of this expression, which is like, we have the derivative of this expression, which is like, it's a step up. It's a really big step up. All right, so now back to our regularly scheduled problem. We have that this is equal to, we still have this part in front. Don't forget it. It's one of those things where you have to keep writing it down or just show that you know it's there. Keep copying in some sense. Times the derivative of x times log of 2x plus 1 minus log of x. All right, now we're ready to take our derivative. And the good news is we don't have to simplify. And you might say at this point, you're like, wait, we haven't taken the derivative yet? No. Most of logarithmic differentiation is setting it up, getting that log in there so that what you have to take a derivative of is not too bad. All right, so, but we're almost there. And with one last push, we should be there. What rule do we need? Well, we have a function, x, times a function. So let's go product rule. I'll take the derivative of the first times the second. So the derivative of the first is 1. So that makes log 2x plus 1 subtract log of x. All right, derivative of the first times the second plus the first x times the derivative of the second. Well, I already take the derivative of log of 2x plus 1. Now here, when I'm taking the derivative of log, I actually like to do the following. Put the function inside the log downstairs. So it's 2x plus 1. And then you apply chain rule. Say, oh, well, what's the derivative of 2x plus 1? It's 2. So the derivative goes upstairs. So function downstairs, derivative upstairs. Minus, we'll do it again, the derivative of log x. So downstairs, x. The derivative of x, 1. And there we go. And since we don't simplify, we stop and say, what a beautiful derivative. Well, depends on your perspective, I suppose. But yeah, not too bad. Not too bad. All right. Number 8. Oh, I'm feeling some words coming on. A hole in the ground. All right, this is probably our hole here. Is in the shape of a cylinder with height h and radius r. See the picture? Nice picture. A special drilling machine increases both the height and radius of the hole at the same time as it drills. That's a pretty good machine. At a certain moment, the radius of the cylinder is increasing at a rate of 1 inch per minute and the height increasing at a rate of 3 in min. You know what? I think they forgot that there's supposed to be a slash there. 3 inches per minute. There we go. We won't tell them. We're amongst friends. If the volume is 20 pi inches cubed and the radius is 2 inches, how fast is the volume increasing at this moment? Include units. All right, I'm going to mark the phrase include units so that I don't forget. Now, when we talk about include units, this is at the end. So we're not going to worry about that at the beginning. That's an end problem. That's a problem for us in a few minutes from now. But for us, what's our problem? Well, we have to start thinking about things. Now, we have a few things that pop out. We notice that we have a cylinder, and we're talking about volume, because we see volume here. And we say, well, do we know the volume of a cylinder? Oftentimes people do, but spoiler alert, it's on the formula sheet. That's right, the formula sheet has volumes for cylinders, spheres, cones. So we'll write that down. We have that volume is pi r squared h. Okay, now what else do we see? Well, we see that there's a radius, and it's increasing at a rate. Oh, rate. That's a good word. And I'm going to mark that. And the height is increasing at a rate. Now, why am I marking the word rate? What's another way to say rate? Derivative. The derivative, right? So we say, oh, I have multiple rates involved. So there's a clue here. Lots of rates are involved in this problem. They're related to one another. What kind of problem do we have? Related rates. Booyah! Yes, related rates. Okay, so let's mark down the rates. We're going to translate what we have. So we have this formula for volume. So let's start here. The radius is increasing at a rate of 1 inch per minute. So the radius, well, that's r. So we say dr dt. That's what's happening with the rate for radius, and it's 1 inch per minute. But I want to point out a key phrase here. It's increasing. So sometimes they'll put increasing and decreasing, and pay attention. So dr dt is plus 1, and I'll just mark it as inches per minute. Now, we don't need that in our computation, but just to emphasize. Height, dh dt, is increasing, so that's a plus, at a rate of 3 inches per minute. And so we have dr dt, we have dh dt, and our goal is find, right, how fast volume is increasing. So find dv dt. All right, so now we have a couple of things. Cool. We have volume, find dv dt, when volume is 20 pi and r is 2. Now, they didn't tell us h. Can we figure h out? Well, we can do it, right? Because we have a formula for that. So 20 pi is pi times 2 squared, which is 4, times h. So if you divide, you say, oh, h is 5. Do we need that? I don't know. But maybe. So it doesn't hurt to write it down. All right. So what do we do? Well, all these are functions of t, right? dr dt, dh dt, dv dt. So what we should be thinking of is like, let's take the derivative with respect to t. So we're going to take the derivative with respect to t of everything. Now, volume, radius, and height are all changing. So those are all functions of t. So when we take our derivative, well, the derivative of volume with respect to time is dv dt. So equals product rule. So derivative of the first, well, derivative of r squared 2r times dr dt. That's a chain rule, right? So derivative of r squared is 2r times the derivative of r, and we're taking derivative of r with respect to t, so that's dr dt. And don't forget the h, plus pi r squared, all right? So that was the derivative of the first times the second, plus the first times the derivative of the second, dh dt. Now, what do we do? We'll plug in everything that you know and see what we have left to figure out. We don't know dv dt because if we did, we'd be done. So we don't worry about that. So we have, okay, so this is pi times 2 times r. R is 2, so that's 2 times 2. dr dt is 1, so there's a 1. H is 5, so that's a 5. Plus pi, and then we have r squared, so that's 2 squared, and the h dt is 3. Okay, so 2 times 2 times 1 times 5, that's 20 pi. 2 squared is 4 times 3 is 12, plus pi makes 12 pi, so that makes 32 pi. Hey, we did it! We found dv dt! Woohoo! Nice! Good job, us! Woohoo! High fives! Whoa! You know, in our minds, we're celebrating as we do this. But wait, that's an unusually large amount of space left for an answer. Did we forget something? Hey, there was something we said we'd do at the end. We need to include our units. So, how do we figure it out? Well, here's the easiest thing. If I want to know what the units of dv dt are, I think about what are the units for volume, what are the units for time. And we say, well, okay, for volume, well, volume is like in inches cubed, because it even says it here, volume is inches cubed. So we say, okay, so that says we have inches cubed volume, right? Units for volume. What's our units for time? Well, we have minutes and minutes. Everything's being measured in minutes. So that's our units of time. So there's our units. Because after all, we don't just want 9, we want 10 on this problem. All right, a perfect 10. Well, that's number 8. All right, let's go and do number 9. Let f of x equal 1 over x squared plus 3. All right, I will allow it. Okay, no. Come on, let's be serious here. Identify the intervals where f of x is increasing / decreasing. Okay, now increasing, decreasing, this part right here, we can figure this out by first derivative. So this is saying, hey, look at what's happening with first derivative. So we say, well, let's get into that. Now f of x, that's 1 over x squared plus 3. You can think of this as x squared plus 3 to the minus 1 if you like. So that can sometimes make it a little bit easier to take a derivative. Or you could just do a quotient rule if you don't want to do it. But here, if I bring the minus 1 down, then x squared plus 3 to the minus 2 times the derivative of the inside, which is 2x. So that gives us minus 2x over an x squared plus 3 quantity squared. So that's f prime. All right, f prime is saying how are things changing. So when it says increasing, that says f prime positive. We're going up, up, up. It's our moment. When we're decreasing, f prime negative. So we say, okay, when can we change? Well, we look for zeros or undefined. Now, we do have a division here, but downstairs is something always positive. In fact, it's always at least 9, because x squared is positive, and I add 3, that's at least 3 in my square. So the downstairs will never be 0. The upstairs, okay, that could be 0 at x equals 0. So we say, that means we're cutting our number line in half. So we have 0. Now, we plug in something to the left of 0. And we say, what's happening at that point? And which point? Do you plug in anything less than 0? Minus 100, minus a million, maybe minus 1. That's pretty simple. Well, if you do that, you get minus 2 times minus 1, which is 2. And downstairs you get 4 squared. And 7 years ago when we started this problem, no. All right. You get 16. Now, you don't actually care about the value. What do you care about? The sign. And you say, okay, so it's positive. Now, what about above 0? All right, pick a value like, say, 1. Plug it in. Upstairs, a negative 2. Downstairs, we'll get 1 plus 3 squared, 16. Again, we only care about the sign, negative. And once you know the value in one point, you know the value in the whole. So we say, okay, this, to the left of 0, we're positive, so we are increasing. And to the right of 0, we're negative, so we're decreasing. But they want intervals. And here is where I'm going to say something controversial, because I know that there are members in the faculty who disagree with what I'm about to say. And the good news is you'll get points either way. So where are we increasing? Well, we are increasing for negative infinity less than x less than or equal to 0. Here's the controversy. Do we include 0 or not? And technically, there's a strong argument to be made. Yes, you include 0, but some people say, no, you don't. And here's the thing. We're going to give you points either way. So don't worry about it. Don't worry about it. Decreasing for, and now this interval, 0 less than or equal to x less than infinity. Now, if you use other notation, like maybe you said, oh, I don't like 0, and I want to use this notation of intervals, that's fine. We would give you that as well. You know, whatever you like, as long as we understand, you're like, hey, it's the part starting from 0 and above, or the part just above 0, right? There's options here. All right, but anyways, that's it. We definitely got the increasing, decreasing. So, part B. Find and classify the critical points. Well, look, we already found the critical points. So we already know the critical point is at x equals 0. There's only one of them, because that's the only place where the derivative is 0 or undefined. X equals 0. First derivative test says what? Well, we are going up, then we're going down. So that says that x equals 0 is a local max. All right, so part A is actually doing the work for part B. Now, part C. Identify the intervals where f of x is concave up / concave down. Now, we're getting to concavity. Now, how is the curve bending? And so for this, we need what? We need the second derivative. So concavity is a property being captured by our second derivative. All right, well, we have our first derivative, so let's take our second derivative. Here we go, f double prime of x. And now this time, I'm just going to go ahead and do a quotient rule. So we're going to take the bottom times the derivative of the top minus the top times the derivative of the bottom. So there's a chain rule here, 2x squared plus 3 to the first times the derivative of the inside, which is 2x. All of that over the bottom term, x squared plus 3 squared, right? You square the denominator. All right, now what can we do? Well, there's a lot of x squared plus 3's. And so we say, hey, there's like 4 of them downstairs. There's 1 in this term, and there's 2 on this term. So we can pull out an x squared plus 3 from the top, and we can pull out an x squared plus 3 from the bottom. We'll be left with an x squared plus 3 cubed downstairs. What we'll be left with here? Well, we'll have a minus 2 times x squared plus 3, right? Because we got one of them, but that means there's still one left. And now here we just start x squared plus 3 and lots of 2's. There's a 2 and a 2 and another 2, and there's 2 minuses. So the 2 minuses become a plus. So that's a plus. So that's good. And what we see, 2 times 2 times 2 is 8. And so there's a plus 8x. Okay. Yes? Oh, no, not 8. X, it's 8x squared, because there's 2 x's. I was so focused on the 2's, I didn't count my x's right. All right, good. Oh, okay. All right. Double check, right? Even I'm nervous about some of these things, so I'm just double checking to make sure I got everything that I needed to get. Okay, all right. So the x squared plus 3's cancel. What do we have? Well, we can distribute. So we have minus 2x squared plus 8x squared. So that gives us 6x squared, right? Minus 2x squared plus 8x squared minus 6, okay, over x squared plus 3 cubed. Well, that's upstairs, that's 6 times x squared minus 1. But wait a second, x squared minus 1 is x minus 1, x plus 1. So 6 times x minus 1, x plus 1 over x squared plus 3 cubed. Okay. Whew. Now, what are we looking for? Well, we're doing the same thing we did in part A, which says, is it ever undefined? Is it ever 0? It's never undefined because we don't divide by 0. Same idea, right? The denominator is not going to be an issue. It is 0 if the numerator is 0, which happens at 1 and negative 1. Okay. So, we now have our points. So we're going to mark, there's negative 1 and positive 1. Okay. So I can push the page up a little bit now. So we now test each point, or each interval. So plug in something big, like 2. And I'm just going to look at the sign. Positive, 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 positive. So f double prime, positive. Plug in 0. Positive, negative, positive, positive. The sign, collectively negative. Plug in something below negative 1, like negative 2. Positive, that's the 6. Negative 3, negative, negative 1, negative, positive. Well, positive, negative, negative becomes positive again. So we're positive. Now, here's the thing. Positive means what? Concave up. Negative, concave down. And positive is concave up. All right. So, with that in mind, what can we say? We can say concave up. Well, we're from negative infinity all the way up to negative 1. And again, you can include and not include it. And from 1 all the way to infinity. And concave down, where does that happen? Well, it's from negative 1 up to positive 1. Okay. And again, you can include or not include the endpoints. All right. Whew. There's not a lot of space for us for that part of the answer. Oh my goodness. Oh my goodness. Now, find the inflection points of x, and then we'll be done with this problem. How do you find inflection points? Inflection points are where concavity changes. So we're like, oh, this is saying we need to go and find where does it change from concave up to concave down or vice versa. And we say, aha, well, concavity changes at x equals negative 1 and x equals positive 1. So it just says find them. So that's how you find them. And you say, look where the concavity changes, and there you go. All right. Nice. Yeah, I will say they like these types of problems. It's not uncommon to see these. In fact, I would say it's kind of a predictable type question because it's like, how do we test on increasing, decreasing, and how do we test on concavity? We'll just make up a function and see how you do. So don't be surprised if you see something like this. Okay, last problem. Our final problem? Really? Yeah, like all good things, the calculus test must also come to an end. So, number 10. A part of a roof is an isosceles triangle. So that's this ABC. And we're told that AC equals BC. Nice. A rectangular region, there's this PQRS, has to be selected to install solar panels. And you are given that A to B is 24 feet. So maybe let's mark some things. So A to B, this is 24 feet. And we're also told C to E, well, okay, that's 10 feet. All right. And now we're said that PQ equal 2x. Okay, see how there's an x and x. And PS equals y. Okay, well, we have all that. Now, using similar triangles, find a formula for the area F of the rectangular region PQRS in terms of x only. Now, let's think of this. Well, our area F, so they want us to use F as area. Well, we can think of it as a rectangle because it's a rectangle. Whoa, cool. That makes it easy. So it's 2x, y. Right, 2x across, y height. So this is width, y is height. And you're like, cool, 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 except it's not in terms of x only. So we're like, oh, we need to replace y by something which has an x. But how are we going to do it? Well, we don't have a choice. We need to use similar triangles. So we start thinking, okay, where's a triangle where y is involved? And where's a triangle that's similar to that? Well, here's a triangle where y is involved. Okay, so that's a triangle where y gets involved. And where's a triangle that's similar to that? Well, I'll use this other side. It's symmetry. It's the same. It looks a lot like this triangle. So these two triangles are similar. Now, what do we know about these triangles? Well, we're not going to use the diagonal parts because those don't have any measurements attached. But for this triangle here on the right, we see that the height is 10 and the width is half of 24. Right, 24 is all the way across, so half of that is 12. Okay, on the other hand, we have the height of the small triangle is y. Okay, and then we have the width. Now, what's that? Here's where we use the magic. Halfway across the base, A to E is 12. P to E is x. So this part right here, well, that's, you take the full distance from A to E, subtract off P to E, so that becomes 12 minus x. 12 minus x. And there you go. There you go. Perfect. Perfect. All right. Now, what can we do? Well, okay, 10 over 12, that becomes 5 over 6 equals y over 12 minus x. And now, move the 12 minus x across. So y becomes 5 over 6 times 12 minus x. And notice, that's y. So we can replace y with something that just involves x. So we say, okay, updating, f, now I'm going to be really explicit and say this becomes a function of x, and it is 2x, the width, times 5 over 6, 12 minus x, the height. And if we wanted to, we can certainly do a few more things. The 2 can go into 6, making it 3. And so we have 5/3 x times 12 minus x. And we could even distribute. Sure, we can do that. Why not? And what do we have? Well, 5/3 times x times 12. Well, 3 goes into 12. And so that will give us a 20x. And then we're going to subtract 5/3 x squared. All right, so there's a nice function. And I cleaned it up because I peeked ahead. And I peeked ahead and it says, find the values that maximize. Ah, okay. All right. Cool. So we want to maximize the area of the rectangle, which means we want to maximize f. So what do? Well, we use our tools we have. We've been preparing for this. And we say, all right, so let's take f prime of x. We're looking for our critical points. So f prime of x is what? Well, it is root of the first, 20, and then subtract. I'll take the root of the second, so that'll be 10 thirds times 2x. Okay. And, well, there you go. So what do you get? Well, this is really, you can factor out 20 thirds. And if you do that, 20 thirds, you'll be left with a 3 in the first term and minus x. All right. So there's our derivative. All right. Cool. Now, set it equal to 0. What do you see? Well, this happens at x equals 3. And, hey, that's not crazy, right? Because it's only 12 feet across. So it's saying x equals 3 is about a quarter of the way across. So it's a tall rectangle. And you might say, wait, is that accurate? Well, who knows? Maybe this picture is misleading. It can be hard to say, but okay. That's what it's suggesting the answer is. Now, we have to unravel this. We're not done yet. So we have x equals 3 feet. Okay. And, all right. Wait, whoops. No, I messed up. Hate when that happens. That's okay. You know, as the great mathematical philosophers say, you should check yourself before you wreck yourself, right? So, what happened? Well, I brought the 2 down and then I did it again. You only bring it down once. Oh my goodness. All right. Hey, we all make mistakes. The key is correct them early and double check and say, wait a second, is that the right derivative? Did I make a small mistake? Because small mistakes are usually the really hard ones to catch, and they're also some of the most important. So here, I just bring the 2 down once. So it's 20 minus 10 thirds x. There we go. And now what can we do? Well, we'll do the same sort of philosophy, but now we'll factor out 10 thirds. So this is 10 thirds. And now, if we do that, what do we have? Well, it's going to become 6 minus x. There we go. And when does this happen? This happens at x equals 6. All right, now, if x equals 6, what is y? So y is 5/6 times 12 minus x, which is 6. 12 minus 6 is 6, and so we end up with y equals 5. So we say, okay, so the maximum happens at x equals 6, and y equals 5. Now, they didn't ask us for units, so we'll leave it there. Now, are we done with this problem? No. We are not done with this problem because there's a statement. Be sure to justify that your values produce a maximum. Now, we can't plug in every other possible combination. That would take too long. And so we're not going to do that. So what are we going to do? That's a great question. What do we do? Well, we say, let's use our tools. We can do a first derivative test or a second derivative test. Now, we haven't done a second derivative test yet. Let's do that. Let's do that. So, if we look at this, we can say, look, f double prime of x is negative 10/3, right? Just taking the second derivative. So f double prime of 6 is negative 10/3, which is negative. So, by second derivative test, this is a maximum. And everything goes downhill from there. All right, now we're done. We're done with the last problem. We worked our way through the whole exam. Ooh, phew. All right, well, good stuff, good stuff. There's lots of things that we talked about. There's some things that we could have been asked but weren't. So make sure you study and practice. The more you practice, the easier it'll be to recognize patterns. We keep asking similar questions over and over again. And we do that because there's a few basic core concepts. And once you say, I can pick up on that, you're going to be great. I believe in you. I know you can do wonderful things. I want you to have a great test. Thanks for joining me. Hope you do well, and I'll see you again. All right. Bye.